Hi, everybody. Today I'm going to do sort of like a Unit 5, Unit 6 preview, and I'm going to do it by talking about this packet that you received before we went on remote learning. And in here, I'm going to kind of highlight what you need to know, don't need to know for this year's test, and sort of where to find particular things and what they represent. So, if you don't recall this packet, I can post this AP Stats Giant packet so you have it. These pages are actually in reverse order, and there's a reason for that. Mainly because when you first got this packet, these were the first couple of pages you saw, and these are all provided on one of the links I gave you from the College Board. Like, this is what you would have gotten the day of the AP test. Now, frankly, I don't know that this is going to be the most helpful to you. Here's how you find an average. Here's the standard deviation. But and I know, you can find those things on your calculator, as well as, R when we talk about linear regression. So you'll see all this, but it might not be worth it to focus on that page. And the same with this one. There's just some stuff about probability and binomial distributions. A lot of that's on the calculator, and even here. Now, up here, this is just a generic how you find a test statistic. It's basically the z-score formula, but again, because it's open note this year, you probably don't need to worry about this. It tells you the basics of a confidence interval, which again, we'll see on the later page. And if it's open note this year, I would probably prefer you use our notes. I think they're a little bit more helpful to you. And a lot of this information here is organized a little better on a different page. So these charts, again, this is basically like normal CDF, which we'll look at a review of that in a little bit. This page is stuff with T-curves, which again, I would pretty much just use the calculator for. And this chi-squared one is not even on the 2020 exam, so I wouldn't even worry about that page. So then we get into this stuff. What is all of this? So those back pages, I'm going to take you actually to the very last page. So this very last page, what I've done here, and you can pause this and kind of take a peek, I've organized this flowchart by unit, because this is basically what AP Stats is in a nutshell. Now, it might seem a little crazy looking, but what they're basically saying is you're always testing data of some kind. If it's quantitative, that's numerical. If it's categorical, that's like words, I guess we've said. But what we've learned is that quantitative just means it's numbers with units. So like feet, inches, it's like hard data. Categorical is usually when we're saying like a proportion of or a percent of. So where these units all break down. Unit 1, the first thing you learned about was here's some numbers or variables. There's always one variable. If you know something about the mean and the standard deviation, you could do z-scores and the normal curve. That was Unit 1, this whole little chunk right here. Now, Unit 2 is where you started to get into two variables. You would do linear regression. You would make a scatter plot. You would do a regression test. If you did a scatter plot that was not linear, this no right here, that's when you'd rescale. If you remember, maybe you take the natural log of y and regraph it, or the natural log of x, or both, or the square root of y, and you would progress through until you were able to straighten out your scatter plot. This is where we learned about residuals and how they could also give you a hint as to whether or not something was linear. And this is all R squared, those things that we talked about a while back. So if I zoom out here, that takes care of Unit 1 and Unit 2. Unit 3 was experimental design. Unit 4 was probability. They're not on this flowchart, but Units 5, 6, and 7 are. Now the good news, Unit 7 is not on the test this year, so cross that out. You don't even need to look at that. Unit 5, what's going on here? This is what we call inferential statistics. You'd make an inference. That means you were maybe hypothesis testing or making a guess about a confidence interval. And proportions is another way of saying a percent of something. So that's like saying, studies shows that 58% of people like Cheez-Its, and then you're trying to disprove that or prove that through a hypothesis test. Or if it's two proportions, maybe it's men and women or two different populations you're comparing. So this information here, one sample or two sample, one prop or two prop, those are always called one prop z-test or two prop z-test. And again, that's all in the calculator. If you forgot where some of those things are, we will look at that momentarily. And even here, Unit 6, this was the one that was almost exclusively remote learning. And that's when we learned about t-tests, which were basically saying, hey, I have quantitative data. I can find the average of my sample, but is it representative of the population? So this is where you learn a one sample t-test or a two sample t-test. What this means, independent or paired. Independent would be like two different samples from two different populations. Paired is when you had something like husband and wife, where there might be a relation and they're not totally independent perhaps in their thinking. Or pre-test, post-test, or before and after. Like there was a speed skating example that showed their times on the inside track and outside track, or you might have said this was their time before training and after training. That's where you would do what's called a paired t-test. But again, the calculator takes care of a lot of that stuff. So what we're going to do in this video is sort of talk about Unit 5 and Unit 6, basics of confidence intervals, basics of hypothesis testing, and where to find them on your calculator. So this page and these pages that look like this, they might be a little bit hard to follow. There's a lot going on here. They kind of throw a bunch and they use the actual formulas. So once you're more comfortable with this stuff, maybe this will help you. I will say here, anything with goodness of fit or chi-squared you can ignore, so you don't need any of that. But this was actually provided by your textbook. And I included it in your packet because what's nice here is that this sort of shows you proportions. That's Unit 5, means that's Unit 6. What's the test you're looking for? One proportion z-test, or two proportion z-test, or one sample t or two sample t. It's kind of telling you what you would look for in the calculator, and then it tells you the estimate from your sample. Remember p hat, or they call it y bar. We a lot of times use x bar. The parameter, this is for the model where you'd see mu. So again, the difference is a sample is a small chunk of your population. Parameter uses population uses parameter. Test statistic, they're writing estimate here. Test stat is from a sample. And these are the standard errors, which are the standard deviations of your sample. Now again, a lot of this formula heavy stuff, all taken care of by the calculator. What this page reminds you of are those assumptions and conditions. So if you've forgotten what those are, you can always look back on this and say, okay, when we're talking about proportions, one or two samples, we always wanted to make sure, remember, things were independent and randomly selected. We always wanted to make sure of that. And what you see here, they write SRS. That means simple random sample. If you have a simple random sample, it's independent and random by default. So this is a quick way of writing that if you're checking your assumptions and conditions. You'll also remember we talked about how your sample has to be less than 10% of the population, but you also have to have at least 10 successes and 10 failures. And that's sort of what this is describing right here. Now, on that other page, if that was confusing you, that's what they're trying to say here. So here's the fancy z-score formula for a sample proportion, and that's what they're saying here. Here's the assumptions and conditions. This NP naught and NQ naught, that's like saying at least 10 successes, 10 failures. Capital N, that's like saying the population, and this is like you saying my sample is less than 10% of that. It's just a funky way of writing it. And then they write SRS here, independent or random. So if you were trying to make sense of this chart, that's what that means. And this gets a little more detailed, I guess, because it tells you how to find the confidence interval. But again, I would just use the calculator. So if you've forgotten your assumptions and conditions, I would use this chart here. They add on the ones for means right here as well, where if you have, if your sample's not that big, like once you exceed a certain amount, this central limit theorem sort of kicks in. So we talked about on another page where if you have a small sample, like less than 5, you got to be careful. You better hope that your sample is almost exactly normal looking. If you have a sample between 5 and 15, your data, and that's what this is saying here, both histograms, you want to hope, like the bigger your sample is, the less perfect the histogram of your data has to be. Because of the time restrictions on this test, I don't know that you'd have to worry about like checking that. They might just ask you about that because again, the central limit theorem basically says as my sample size gets larger, the it will inevitably start to approach what the model looks like, and it will approach a normal model. Okay, so this was a lot of charts. Really, the nitty-gritty of what we're talking about can be found on this page with the acronym for a confidence interval and this page with our acronym for hypothesis testing. And I added some notes onto these pages to help you out. So getting back to a confidence interval, I'm almost positive you'll be asked to hypothesis test and find a confidence interval. The good news is the P and the A and the N in both phantoms and panic is relatively the same thing. Parameter is just a way of you saying what are you looking for, and you're going to be testing whether or not a sample proportion or a sample mean is greater than something, less than something, or in this case your parameter, if it's a confidence interval, you'd say I'm looking for an interval in which to find the true proportion of the population or the true mean of the population with this much confidence. So that's what your parameter always is. Again, assumptions and conditions, they're relatively the same. If it's proportions, that's where you're talking about, is it independent and random? Is it a sample that's less than 10% of the population? Are there at least 10 successes or 10 failures? If you were doing a confidence interval for a mean, oh, pardon me, trying to get back up to here, you can see here that confidence interval for a mean, same idea. Is it independent and random? Is the sampling distribution approximately normal? So again, this says right here, central limit theorem applies when n is greater than or equal to 30. So if you have a sample that's big enough, you won't have to like check it in your calculator and see if the histogram of your data is unimodal and symmetric. You might be given a word problem that just says, I have a sample size of 50. Then you would know that central limit theorem has kicked in, and that would be like you would kind of just say that in your assumptions and conditions. Something to note over here in case you're like, what's the difference between these two? If you know the parameter, if you know sigma, the standard deviation of the population, you would use a z-score, but most often if you're sampling, you only know S, the standard deviation of your sample, and therefore you would have to use a t-test, which would be right here. So this is more often what you would see. All right, but you'll notice the assumptions are the same. Now back to this page here with panic. You're going to be told what you're looking at. You're going to know if it's, let's say, a 1 proportion z interval because you're talking about proportions. You'll know if it's 2 samples or 2 proportions, and you'll know if it's talking about means or not. So this is where you would just say, I'm going to use a 1 or 2 proportion z interval or 1 or 2 mean t interval with this much confidence. The basics of a confidence interval. It is basically just a test statistic of some kind, plus or minus what we call the margin of error. And that was seen on one of these formula sheets back here, where it said confidence interval statistic. That's again either a sample proportion or sample mean, plus or minus. Now this whole piece here is what we call margin of error. It's a critical value, either z star or t star, times the standard deviation of the statistic. Now, if I click back here, again, that's what this is. This is for proportions right here. So I wrote a little note here if you want to pause and write this. Margin of error when you're talking about proportions is z star times this, p hat q hat over n, its square root. That's the standard error which is the standard deviation of your sample. If it's sample means, we use what's called T star. And the good news, if you're kind of like, well, what's Z star or what's T star? A lot of times when you do these in a calculator, you really don't have to worry about it. So if you're dying to know and you really do want to know, I talk about that down here. The only reason you'd have to know that is if they said to you, the margin of error for this problem is blank. Find, let's say, the sample size. So you'd be setting this second chunk here, the critical value and the standard error, equal to a margin of error in solving. That was something we saw in word problems a lot. And where that could be tricky is the calculator doesn't have that as a shortcut. So what I mentioned here is the value of Z star or T star is always determined as if you're doing a two-tailed hypothesis test. And one way you could find that with your calculator is you can literally just find the confidence interval, take the upper and lower ends and subtract them, and then subtract either the p hat or x bar value. Now, if you're still kind of like, huh? If you remember, a while back we talked about one-tail and two-tail things. And basically, I'll go find it on here. This was in an old video where I said to you, the values you're sort of looking for, they kind of have to do with alpha and beta, and we'll get into that. But if you're ever not sure what to use, remember, on this chart with t-test, if it was like a 95% confidence interval, you always act as if you're doing a two-tailed thing. So 1 minus 95, that's 0.05, divided by 2 is 0.025. You would find 0.025 and go all the way down to where it says infinity, and that would be the critical value you'd be using. And that's for proportions. Now, if you were doing a confidence interval for means, you would still do this step, but maybe you wouldn't have as big a sample. So that's why it's not Z star when you did those, it was T star with a little n minus 1, where n minus 1 is the number of degrees of freedom. So if, let's say, you had a sample of 10 things and you were finding a confidence interval for the true mean, 10 would be n, so the number of degrees of freedom would be 9. So you would look for 9 degrees of freedom, and then you would look for the confidence number associated with it. So if you were told it was 95% confidence, sorry, wrong chart, you would do 1 minus 0.95 divided by 2, that's 0.025. And if it was 9 degrees of freedom, you would line those up, and this would be the critical value you would be using. Now again, the only reason you would need to know how to find the critical value, which again, you learned are almost always 1.96 for a 95% confidence interval and 1.645 for a 90% confidence interval. The only reason you would have to know that is if you were exclusively asked about margin of error. If you weren't, and again, if a lot of this confused you, don't be scared. Let me show you on your calculator. So, stat, tests. There's tests and there's intervals in here. So if you were asked to find, let's say, a confidence interval, it would probably be listed as 1 prop z interval. So don't go to option 7, you go to this option. You just tell me x would be like the numerator of a proportion, n would be the denominator, and you put in the confidence and that's it. You don't have to worry about z star. Or if we went to stat, tests, and I picked, let's find a t interval. Let's do that one. You're either going to be given the summary stats, which means the sample mean and sample standard deviation and the sample size, and that's it. Or you'd have to physically enter the data into a list and then do it. So you don't have to really know T star, Z star, unless you're asked about margin of error. Now, if you're asked about margin of error, let's just make up a problem. Let's say the average is 2 with a standard deviation of 0.045, whatever, 10's the sample size. And I arrow down to calculate. you're going to be given an answer. So this is the lower and this is the upper end of your 95% confidence interval. You would say, if you had to interpret this, you would say, I am 95% confident the true mean is between 1.967 and 2.032 with 9 degrees of freedom. Like you would just say that. So what I was trying to imply over here was if you have a situation where you're asked about margin of error, which remember is this second chunk, it's either z star or t star times the standard deviation. A common question is, what's the sample size? Well, you would basically have to set margin of error equal to this and work backwards. But there's like a workaround. And what I just did, the confidence interval I just found, if I took the upper minus lower and subtracted off the sample mean, if I had done 2.0323 minus 1.9677, that would tell me the length of my interval. And if I were to subtract 2 off of that, that would equal the margin of error. And then you could kind of proceed from there and solve it. So if there's some confusion again about where those things came from or what they mean, know that a confidence interval, this kind of sums it up right here. You are always trying to say, I am some percent confident the true either proportion or mean of our data is between, of the sample or of the population is between lower and upper. And then what a confidence interval means is what I just said, or if we were to continue to sample in this way in the long run, this percent of the samples would capture the true parameter value as well. So a confidence interval is oftentimes a natural follow-up to a hypothesis test because it's giving you a range of possible answers for the true like parameter you're looking for, whereas a hypothesis test is a way to actually determine, like with a probabilistic method, how likely that answer is. So let's take a look at that briefly, and then that'll be it for our little preview here. So the acronym we used for that was phantoms, and you can see again, P is the same idea, H is different. You always state an H naught or null hypothesis and an alternative H sub A. Now remember, if you're trying to prove your sample that you found is different than something, that's when you'd write your alternative equals this. You'd say it's not equal to some number. That means you're going to be doing a two-tailed hypothesis test. If you're trying to test whether the alternative is greater than or less than a number, you'd be using the greater than or less than sign, and that's like a one-tailed test, which we'll get into in a second. Same assumptions and conditions. Now, the name of your test, just like your name of your interval, it's either 1 proportion z test, 2 proportion t test, or whatever the case may be. Now, test statistic, that's sort of like a z-score. Again, that is literally found on the calculator. You don't have to worry about that. The p-value is also found on your calculator. What is the p-value? It's the shaded area under the curve less than or greater than your test statistic, depending on sort of what you're looking for. So the p-value is almost like the amount or area under the curve between a critical value and the rest of your curve, and we'll see that in just a second. Remember, if your p-value is lower than the alpha level that you set for it, if the p is low, the hoe must go, you would reject the null, and if it's not less than that, you would say fail to reject. Never say I accept. All right? And then, again, your summary, don't just say I fail to reject. You would say I fail to reject, therefore there is not statistical evidence to suggest something, or you'd say there is statistical evidence to suggest something if you did reject. Now, what am I sort of getting at with this whole p-value thing and whatnot? Well, what is basically happening is a p-value is sort of like this proportion. So you determine a test statistic value and you plop it on here. And the p-value is like saying, what's the probability that what I just observed would occur, just by random chance. And you're trying to find a certain proportion. So you're hoping that maybe your guess lands here. If it lands in this critical region, that's when you'd reject. because the p-value, let's say, is 0.05, and you get something smaller than that. So you're landing in this area. But if you get something bigger, you'd fail to reject because you aren't in this critical region right here. But the easiest way for us to understand and interpret that, if you want to ignore charts, is to just use your calculator. So again, what we would do is you'd be given either, this is where you would go to stat tests again. Maybe you're looking at 2 samples of quantitative data, and they give you the summary stats. They say the mean weight of females is this with the standard deviation in a sample of 10, and in males it's this with this standard deviation in a sample like this. You would either enter all that in, and then when you make your way down, this is where you would determine your alternative. Am I trying to prove that males and females have different weights? I would just pick this. If I'm trying to prove that females weigh less than males, I would pick this. Or greater than, I would pick this. Pooled, remember, is if you know the data you're pulling from are of like equal population types and sizes. A lot of times pooled is used in a before and after sense. Like if you were comparing again the pre-test and post-test scores of something, you would pool them. And there's a lot of stuff on those charts that explains that by hand, but you can see how easy it is just to click it. In this case, because it's male and female, I would not pick that. They are different groups, so I would not pick pooled. Or maybe you're doing a hypothesis test and you want to determine the the difference in 2 proportions. So a lot of times when you have 2 of something, like 2 proportions of 2 different groups, you could either enter them in separately here, or you could take their difference and enter them in as a single proportion as well. So it kind of depends on the context of the question. But you can see here, if x and n, that's like saying numerator and denominator for group 1, numerator, denominator for group 2. This kind of does it all. So I'm going to make something up. Let's say 35 out of 50 kids like pizza in Mr. J's class, but only 12 out of 40 like it in a different class. And I'm trying to see if there's a difference of opinion on pizza. So I'm just going to keep it as not equal to. I would calculate this, and what this tells me, again, there's a lot of ways to interpret this. We learned that to be significant is usually a z-score beyond 2 or negative 2, or a p-value that's typically less than 0.05. Now, they usually tell you some amount it has to be less than, but if they don't, 0.05 is safe. How I would interpret this answer, I would say my p-value is so low. Don't write e-4. You'd say it's 0.00016. Because my p-value is so low, my null hypothesis, and again, your null is always that things are equal or that 1 is equal to a given number. The alternative in this case was that they weren't equal. Because my p-value is so low, I would reject that original claim, and I would have to, I failed. I would say I reject it. I'm not saying I accept the other. I'm just saying I'm rejecting the null hypothesis. There's evidence to suggest that the proportion of people liking pizza in one class to the other is different. And again, how you came to that conclusion, you have a test statistic that's so far out there, you have a p-value that's so low, and again, that's how you interpret those things. So this is always the test statistic, and this is the p-value. If we had done this with means, so let's say it was 2 samples z-test, and again, let's say and this one I have to know a standard deviation. Let's say that implies we know it, so a lot of times we don't know it. So let's see if I can find a better one. 2 samples the interval, t-interval. Let's just do 1 sample t-test. So let's say the average amount of that a boy weighs is 150 pounds. In our sample, it was 168 with the standard deviation of 3.5. And our sample was 45 people. And I'm trying to figure out if my sample, now how about I'm trying to find if my sample is greater than average. Well, again, the test could tell you right here, there's your test statistic. You would say test statistic is 34.49. This doesn't follow that 2 and -2 rule like a proportion does, but this p-value does it for you. This is insanely small. This is basically a p-value of 0. So again, in this case, you probably would have said the null is that my group is equal to the average, and then the alternative is that our group is greater than the average. And you would, again, reject that null in this case and say, you know what, there's evidence to suggest my group is above average in weight. Now, a way you can always verify your answer is with a confidence interval. They could very well ask you this on your test. Then what's cool is if you did a t-test or z-test, you just go to interval and it already has your information. Now, let's say we're trying to find a 95% confidence interval for the true mean weight, okay? So what you would say here is that from my sample, the true mean is somewhere between 166 and 169. All right, so if that's the case, we are 95% certain the true mean is here. That's further evidence to suggest my group is above average. You know, because there was a chance that maybe we just happened to sample a group that had like some outliers and it really pulled the average up. But if we're 95% confident our sample's true average weight is in here, that's way off the 150. That's like a way to back up your answer. Or similarly, if we looked at sorry, it's taking a while to get down there, a z interval, if we had said something, oh no, yeah, let's say, well, that's not what I wanted. Sorry, trying to find what we originally did. Let's click here. So remember how we were talking about men and women in a group and we were saying 35 and 12? Let's say it's 35 out of 50 and 12 out of 40, and we're trying to find a true answer here. This would be like saying the true, difference in proportions between these two is around here. So if men and women were truly like equal weight in these two groups, or proportion of them, depending on whatever your parameter was, if you were trying to prove there was no difference between two groups, you'd want 0 in your interval. Here, you can clearly see there's a positive difference between the two groups. So again, what I'm trying to do here, I'm throwing a lot of stuff at you. I'm trying to remind you how a low p-value or a very large test statistic in the positive or negative for proportions or in the positive for t-tests can be an indicator that you would reject the null hypothesis. A way to back that up is to verify it with a confidence interval. If there was no difference between two groups, you would expect 0 in your confidence interval. And if you were comparing just one group, you weren't comparing two, you would hope to see the parameter value in your confidence interval. If it's not, then there's evidence to suggest your sample is either really big or really small and does not contain it. Now, we will see that more with practice problems. I just wanted to remind you of where all these things are on your calculator. A couple other things to note while we're talking about calculators. These two charts right here are talking about z-scores. This is basically normal CDF. So if you wanted to determine the amount of area under the curve, let's say you were trying to find from a z, like what proportion of people are less than a z-score of 0.4. Okay, well, here's a z-score of 0.4. It's 0.6554. What that's saying is the area under the curve up to that amount is 65.54%. What that is like on a calculator, though, particularly I would use a calculator if you have to go between z-scores. Like if they said what proportion of people is between 0 and 0.4, you're subtracting these two. But to kind of avoid that, normal CDF, and that's not found in stat, that's found in second bars, that's under distributions, you would pick as follows. So to verify it, the lowest z-score you can think of, that's where you'd say like -9. Upper bound, let's say it was 0.4, and you would keep 0 and 1. On your test, if you were writing this, you'd want to say using normal CDF with a lower bound of -9, an upper bound of z, like of z equals 0.4 and z equals -9, where my mu is 0 and sigma is 1. The area under the curve is this. So that would be like a way to explain what you just did without having to use your chart necessarily. Now, the other last thing I want to talk about here, we talked about having a p-value that's lower than 0.05. And again, 0.05 is kind of like this default. Technically, alpha is this. Alpha is either given to you, or we typically pick 0.05. But alpha is, everyone, also the same as the probability of a type 1 error occurring. So what that means is 0.05 might mean there's a 5% chance we make a type 1 error. So that means that if we wanted to reduce that likelihood, we would inevitably increase the likelihood of a type 2 error. So again, to kind of repeat what I just said, if the null is true and we reject it, that's why we need a p-value that's low. We don't want to make a type 1 error. We want a false null hypothesis to be rejected. That's like our goal. And that's what we call the power of the test. In the event that H0 is true and we reject it, then that would actually be like an error. We don't want that to happen. If it was true and I failed to reject it, that would be better. So we set this threshold of alpha so that we don't make mistakes, and 0.05 is like an acceptable amount usually. If it's coronavirus testing or something like that, that might be 0.01. You might even need a smaller alpha. So in order for you to really reject your results, you have to have a really significantly small p-value. Now, alpha and beta, we talked about them being inversely related. If you increase the likelihood of a type 1 error, you decrease type 2 and vice versa. We talked about how the power of a test is basically a test's ability to detect a false null hypothesis. And if you want to increase the power of your test and make it stronger, you'd have to lower beta, because 1 minus beta would make this bigger. But if you lower beta, you increase alpha. And something we talked about was the only way to increase the power and minimize increasing any type of error is to raise your sample size. So to bring this full circle here, that's what you're seeing in real life right now. People don't want to have type 1 errors. They don't want to have a test telling them that they have a virus and then they reject it and say they don't. Nor do you want a test telling people they don't have it when they really do. So you're trying to find this delicate balance between the two, and the only way to account for those two types of errors and minimize their impact and increase the power and efficacy of a test is to sample more people. Now, one other thing mentioned here, effect size. This is the actual difference between your null hypothesis value and the true value. Again, that is mainly if you knew the actual value. It's like saying how far off is your sample from your hypothesized amount. So if effect size gets larger, it becomes more obvious how far apart they are, and it would be obvious when you hypothesis test. If you have a small effect size, it might be more difficult to accurately weed out if something is an error or not, because the true answer isn't that far off of your null. Now, this was a lot of theoretical talking. This is a lot of just me showing you things. I'm hoping this just refamiliarized you with where things are in this packet. I hope seeing all of this helped you a little bit and refresh your memory. What I'll do with my next video is we will look at the Unit 5 and Unit 6 answer key, and I'll walk you through it and remind you of both the confidence interval and hypothesis test way of answering these questions. And then we'll start getting into just practice material. So I understand that a lot of you have a lot of AP tests this week. Luckily, you had the chance to learn this still and still review it. So what's coming in the future? Later this week, I'll have the Unit 5, Unit 6 answer key videos. Then I'll start sending you practice questions that we will practice submitting through the Practice AP demo site, as well as emailing them to me so I can grade them. All right, best of luck if you have any tests this week. I'll be talking to you soon.